It is quote unquote clear, but we don't know what content is going to be in it. Yeah, it turns random. Yep, yep, yep. So this type of RAM is called a static RAM, which is also not the kind of RAM that is used in most computers, but it is a lot simpler to understand as compared to a DRAM or dynamic RAM. Yep. It depends on that part. It depends on the operating system. It is not a hardware thing. It is an operating system thing. So if you properly shut down everything, then it will save the state of everything and correctly shut down everything so that you won't be you won't be in the middle of, let's say, writing to a file when the operating system shut down correctly. On the other hand, if you have a laptop, not a laptop, a desktop computer that has no battery backup, you just go to the socket and you just yank the cord out of the socket, then you might be in the middle of a file write operation, which means you can potentially lose some content in the file system. Now, how much you can lose depends on the file system itself. With more modern file systems such as NTFS, extension 3 or 4, or anything up, than that, and also the file system of a Mac OS, a modern Mac OS system, they're called journaling file systems, which means before the actual file operation is performed, the system will write a very small journal entry to remind itself, oh, I am about to do blah. So if power is shut off right at that time, the operating system would actually know, oh, okay, before I was shut down, this was what I was about to do. Now, would you lose the content of that one file that is in the process of being written? Chances are yes. Okay, you might lose the content of one single file, which is not bad at all. Okay, because the alternative is to have something that is like a fat file system, which is file allocation table file system. In that case, you can lose a bunch of files, when you shut down the system without, saving everything first. ZFS is going to be safe for sure. ZFS is developed by IBM, and IBM, for the most part, deal with enterprise level file systems, so it's going to be like super safe. That part I do not know. I do not know, what you mean by healing itself. Most file system has some kind of utility program that you can run in order to detect whether there are problems or not. So whether it can be done automatically or, something that you actually have to run a command to run, that part depends on the operating system. All right. So let's go ahead and play with it. Yes, go ahead. Yes. Yes. So the question is, when you're trying to run an executable, what is happening, right? So, I'm just paraphrasing your question. So the executable is existing as a file in the file system, which means it is not in RAM. Okay. Um, so when you run a program, when you double click on an icon in Windows to try to run the program, what's happening is the operating system will read the executable, and then the operating system will try to see if there's enough space in RAM to fit the program. And then the loader, which is a part of the operating system, will now say, oh, okay, so I see that this executable is going to be loaded into this portion of memory. Then it has to go fix up a bunch of locations, because the executable is designed so that it can be loaded into different regions of memory. So if you decide to load it here instead of here, there's a bunch of things it has to fix up. The loader will fix it up. Okay, the question is it contiguous or is it not contiguous? So the answer is, you're gonna like this. It depends on what you're talking about. So if you're talking about um, a specific segment, then logically it is contiguous, but physically it may not be. which means because modern operating systems have virtual memory, which essentially says, okay, we only have 16 gigs of RAM, and your game is going to take 32 gigs. Okay, so are we not going to run the game? No, no, we're still going to run the game. Okay, but we'll only try to fit the portion that is in use into RAM. Okay, so if at any time the game that you're trying to run only about 80 gigs are actually needed in RAM, then having 16 gigs of actual RAM is more than enough. Even though the game executable itself or when it's running, it might take up like 32 gigs of RAM. Because if you don't need all 32 gigs at the same time, then not the file system, the operating system can page in and page out portions of the RAM in order to say, oh, okay, I see that we don't need this page for now. I'll swap it onto the hard drive, save it for later, so that I have room for something that I need right away. So that's a fairly advanced, concept. Virtual memory management is a fairly, kind of complex concept because it's not just the hardware that needs to generate what we call a page fault. The operating system also needs to know how to deal with a page fault. So this is the main difference between how I teach this class and how Berkeley wants this class to be taught. Because Berkeley wants to get into virtual memory, they want to get into operating system concepts, and that's how they want to use up the time for a class like this. I want to go opposite direction. I want to talk about how you design logic gates, how the most basic adder and subtractor is made, what is behind binary number comparison. I want to get into the low level details in this class, so I won't have time to cover the concept that Berkeley wants. So if you want to transfer to Berkeley, this class does not transfer to Berkeley. The same class at Diablo College does, because they actually go over the virtual memory. They basically designed that course to be transferable to Berkeley. So different philosophy. I want to focus on the fundamentals, and then Berkeley wants to focus on the more advanced, concepts in computer architecture. All right. Any other questions before we continue? We got time. Yep. LD being 1 is a read operation. LD being 0 is a write operation. Reset is CLR. When CLR is a 1, then all content locations will be reset to 0. Okay. All right. So now we're going to play with it. So now we need a bunch of input pins. So both A and D in this case are 8-bit. Okay, that's just coincidental. That's the default, but it's coincidental. So I'm going to change both of these to 8-bit, like so. And for now, I'm going to make a straight connection between these things here, and then we'll make a whole bunch of input pins, one for select, which is essentially enable. Okay, so even though it says it's select, it is more like enable. And then we have the clock pin, which is doing what clock pins usually do, controlling the timing of updates. And then we have another one to LD, which specifies the direction of operation. Are we reading or are we writing? And then we have one attached to clear so that we can zero the content of the entire RAM component. So now we can do some experiments. Yep, go ahead. You don't have an option of whether you have a clock or not. The clock is always going to be there. Uh-huh. Yes. Okay. You do not need the clock one. So the only difference between a clock pin versus an actual input pin is the clock pin can be controlled by auto clocking, or when you if you go to simulate and then you say auto clock, or I cannot remember the name. Let me go check. There's a specific name they refer to it. Okay. So if you say tick enabled, then a specific clock pin will toggle automatically based on the tick frequency. So, right. And then the input pin does not, a general input pin cannot do that. But for the demonstration today, right now, I'm not going to use the auto clock. So as a result, I don't need to use an actual clock input pin. A normal input pin is fine if I just manually want to, control the state. Yep. All right. Very good. So now we have the chip being disabled, and to do something that's interesting, let's go ahead and put some actual content into RAM. So you can do that in two ways. One way is something that you learned already with the ROM. You use the poking tool, and then you just poke a location here. It will turn into a red rectangle, and then whatever you type now as a hexadecimal number will be entered at that location. Okay, so if I type in uh, EF, that becomes the content at that location. Now, obviously, this does not reflect typical things that you should be doing in a circuit because this simply allows the end user to specify content in RAM in case you need to do something like that. Okay, but when the program is running, it will be the circuitry that is doing all the changes and not you interactively changing the content of RAM. All right. So the other way to also change the content in RAM is to right click on it and then you go to edit content. So now you get a window that is very similar to the one that you saw on Tuesday, except this one is for the RAM and you have all the italic numbers on the left hand side. Those are the locations of the first location on each row. Okay, so let me tell you what I mean by that. So I'm going to go ahead and change the content of one random location. Let's say this one over here. Okay, so I want to change this location to let's say B5. Okay, because Babylon 5 is one of my favorite science fiction movie or TV series. So I call this B5. Now the question is, what location is that? So you use the leftmost column. Okay, so you look up the leftmost column. This is a A0. So that means A0 refers to the leftmost location on that row. So if this is A0, this is A1, A2, A3, A4, A5, A6, A7, A8, A9, AA, AB, AC. This is location AD. Okay, so we'll go ahead and kind of jot down this, okay, because I want to access location AD. I want to read that location later on. So I am just going to use a text tool and help myself remember location AD is what I need to access later on. Okay, that's just for me for this demonstration. Okay, so generally speaking, you don't have to do a single thing. It's just me, wanting to do the illustration that I need to remember that. Yes. The select is only one single bit because remember, the so-called select port of RAM is more like enable. It really is just saying, okay, is this chip active or not? That's the job of the address port. Yep, yep. So I'm going to demonstrate just that. Okay. So let's just say that we want to access the location that I changed, and it is supposed to be location A what D, okay? So that's what we want to do that, okay? And the first thing I typically do is to specify the address with the address port without turning on the chip yet, okay? So I would do a AD. So A is 1010, okay? So we specify 1010, and then D is 1101. So nothing is happening, right? Nothing is happening because the select port is a zero. The chip is ignoring all the input pins, okay? It's not paying attention at all. It is just pretending I'm not even here, okay? I'm not responding to anything. So the next thing I want to do, because I want to set up everything before I enable the chip, okay? Because by the time the chip wakes up, I want everything to be specified already. So now I need to change LD from a 0 to a 1, because this is a read operation. I want to read from location AD in this particular RAM. And the last thing I need to do is to turn select into a 1 to basically say, okay, I got everything set up already. You wake up and you just go ahead and read location AD and reflect the value of AD with at the data port. So now I just turn the select port to a 1, and then the outputs the content at that location. 0101 is a 5. 1101 is a, let's see, this is 5 and this is a D. It's a 5D. It's not the B5 that I thought I entered. Okay. Maybe I accidentally typed in something. Since everything is being recorded, I can always kind of go back and figure out, why is it not B5? Because I thought I said, that's my favorite, sci-fi. Anyway, but it still shows you how we read a location in RAM. So I'm going to pause right here and try to relate all of this to one operator that you learned in CISP 360 that you might be going like, I have no idea what this operator means. It is the dereference operator. It is the asterisk operator as a unary operator. That's basically what we do. Okay, the address is whatever you are dereferencing, and then the data port is whatever is at that location. Go ahead. It can be seen as an array, but to relate it back to CISP 360, I would just look at this as locations. So each one, so right now I'm specifying um, AD as an address, and at that particular address, we have the content of 5D. Uh, yes, go ahead and then back over there. Go ahead. What input pin? Right now, it is just an output pin because the operation is a read operation. So when we specify a write operation, that automatically changes the direction of the data port. Go ahead. No, the address is serving the address is feeding the address port, but the data port is reporting back the content that is specified by the address port. Oh, okay, so let's talk about the ampersand thing. Okay, in assembly language programming, everything you always have to start with an address, and sometimes the address is all you want, which is okay, cool. But most of the time, you don't care about the address. You want to know what is at the address. So what you see as an extra operation using ampersand is actually, oh, we have to get this anyway. Okay. So in assembly language programming, you always start with the address of the content, and sometimes that's all you need. Okay, cool. We just deal with the address. But most of the time, you want to know what is at the content. Then you have to dereference the address. No, Nope. There's no ampersand. There's no address of when you just look at RAM as a component. Yep. But to summarize, what we have accomplished so far is we are reading the content at location AD. In other words, we are dereferencing using the asterisk symbol. We're dereferencing the location of AD. Now, if you are a syntax, you know, if you cared so much about syntax, then you probably want to add 0x to specify that AD is not the name of a pointer. Instead, it is the hexadecimal number AD that we are referring to here. And then the equal equal is important because I'm just saying that, oh, I just read the location AD in hexadecimal, and that turns out to be 5D as the content. Okay, are we doing okay so far with the quote unquote pseudo C code documentation of what we have just accomplished? We all good? Okay. Does that help a little bit in terms of understanding what the dereference operator actually does in CISP 360? I hope so. And for people who have not learned C++ and only Java, I'm just going to say I'm sorry. Not in the sense that I'm apologizing. I'm just sorry that you did not learn C++ or C first, because without understanding the dereference operator, which is in C++ but not in Java, you would not have a good understanding of what I'm really just talking about. Are we good so far? All right, cool. So now we're gonna do something else. Okay, okay. So I'm going to change the label here. Okay, so we'll go ahead and get rid of this label. Okay, well, okay, I'm not going to get rid of it yet. Okay, but instead of doing this, I'm going to document what I want to do first, and then we'll go ahead and do it. And then you go like, oh, something is not working right. Okay, so what I want to do now is to specify the opposite. Okay, I want to change the content or the value at a certain location to something else. Okay, so I'm just going to say I'm going to dereference location in hexadecimal, let's say DC, and I want to change that to the content of um, mm, trying to think of something that's that's fun to do. So I'm going like mm, yes, go ahead. Say that one more time. Nope, not in a single operation. You need registers for that. Okay, so I'm going to change the location or the content at location DC to hexadecimal BA. DC, refers to DCU, okay, and then BA is the abbreviation of Batman. Okay, so yes, this way I can easily remember what I'm about to do. Okay, so that's what we want to do. Okay, so we get rid of this. And now we go like, okay, let's reset everything and see and try to determine what to do. So to disable everything, I'm gonna disable select first. So now the chip is not paying attention at all. Then I can turn off everything, and now we have to kind of rethink about what to do. So the first thing is, whatever you do, you need to specify the address. In other words, where am which location am I going to do something to, either reading from or writing to? Okay, so in this case, it is DC. So now I need to specify DC in binary. So DC is a 1101. Okay, that's D. C is 1100. So that's the actual location. Now I need to specify, the actual content, the new value that I want to specify at the location, which is BA. But I can't do that with an output pin because the only thing an output pin can do is to tell you the content on the wire that it connects to, but it cannot specify the content to the wire. So that means I think we need another input pin in this case, which is correct. Okay, if you think we just need another input pin, you would be correct. So now I need to go here, pick up another input pin, make it a bit wide, and then have it to connect to the same place over here. Okay, which is not a problem. Okay, we don't have a problem yet. Okay, I'll show you what the problem is later on. And we want to specify BA in this case. So I hope some of you are starting to be able to do the base conversion without looking up a table. So BA is 1011, that's B, and then A is 1010. So if you can do all this conversion in your head, even if it is taking you a little bit of time, that's a good sign. Okay? If you I mean, most of you probably have to go through base 10 first. So you have to say, okay, what is BA? B is 11, and then A is 10, okay? Because we run out of digits when we try to specify the value of 10. You go like, okay, but what is 11? 11 is 8 plus 2 plus 1, and that's why it is 1011. And then A is 10, which is 8 plus 2, which is 1010. So this is the kind of thing you have to do, okay, like all the time. Okay, don't just look it up, don't just wait for me to tell you what a bit pattern is. Try to actively derive the bit pattern, even though you're just sitting here. Okay, just go through that mental exercise, because the more you do that, the quicker you can understand base conversion and other things that connect to these concepts. Yes. Yeah, yeah. So we'll finish the operation. So just give me some time to finish the operation. So now I need to say, okay, this is a right operation. So LD needs to be 0. Okay, so this is correct. It is already a 0. The clock pin is a 0, which is cool so far. Okay, because I needed to be a rising edge in order to update the location. So I got everything that I need to set up already at this point. So now I can turn select to a 1, and basically I'm telling the RAM component and say, okay, wake up and pay attention. All right. So you can see that it has waken up, it has awoken, and then it's looking at location DC already. That location is now selected. But the update is not happening yet, because the timing of the update is controlled by the clock, a rising edge of the clock. The clock is low at this point, but the moment I click the clock input pin, it's updating it, because the clock going from 0 to 1 controls the timing of when we want to update the location. And the location is already specified by the address port. The new content is already specified by the data port. The direction is already specified by the LD port. So the clock pin is just saying now. Yes, go ahead. Yes, that is correct. The clock pin is only relevant when you are updating, just like with a register. Yep. The clock speed. Okay, so that's a pretty complicated question for two reasons. One is this is what we call a static RAM. Okay, you don't need to dynamically re-update the location or refresh the locations. It is a lot simpler to understand compared to DRAM or dynamic RAM. Um, so that's the first part. Okay, the actual amount of time for something like this to happen is actually really long compared to the actual clock speed of your processor. So if you buy a medium end processor these days, what is the clock speed? 2 point something gigahertz. So we are definitely in the range of 2, 3 ish gigahertz, right? Okay. When you buy RAM, what is the specification of RAM? There are several numbers. Okay, there are actually many numbers. The uh, what is DDR, by the way? Okay, because now you have DDR4 or DDR5, but what does it mean? What is DDR itself? Double data rate. That is correct. Double data rate. Okay, So the way it works is if you're reading or writing one location at a time, then every single time you want to read a location, you have to do all this, okay? You have to re-specify the address, okay? And then the chip in response to you changing the address, even if it is increasing by one, takes a long time, and that's what the 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 wait states is about. When you try to buy RAM module, there are wait states involved in reading, writing, setting up the address, and there's a whole bunch of different wait states. So the wait state has to be specified because the moment you change the address port to DRAM, especially with DRAM, it takes a while. Okay, in order for the chip to actually go like, oh, okay, this is the row and this is the column that you want to access. It takes a while. So that's why it is so slow. Okay, your RAM is very slow to access compared to other components that are inside the actual processor itself. Yep, that's cache. Okay, but let's finish that double data rate first. Okay, so double data rate is not just doubling these days; it is actually quadrupling. Okay, so double data rate means um, you're not only accessing something when on the rising edge, but you're also accessing something on the falling edge. And the way that works is there's an understanding between the processor and the RAM component. So the processor says, okay, I'm going to specify the address A at and address once, and then after this, for every rising edge, you give me for every rising edge and for every falling edge, you give me the content of consecutive locations. And the processor says, I'm not going to have to re-specify the entire address. That saves time, okay? And the RAM module itself maintain a little counter internal to it. So it just says, oh, we're just incrementing the address by one, get the content, stash it to the data port, and wait for the next clock to happen. Yes, yep. So it correct. So it usually reads like a chunk of memory. It's not just a few locations. I cannot remember the term. We'll call it the page. Okay. So it will read a certain a quantum of number of locations, and this is called burst mode reading. So you set up the address once, and then the clock goes like like that, and then for every edge, it is the RAM component is clocking in or clocking out the content of the locations. So that goes a lot faster than having to read one location at a time or writing to just one location at a time. The time that you're saving has to do with the RAM component itself is maintaining a counter for the address and go like, oh, I just need to move on to the next location. That's a cheap and quick operation. You cannot tell. So there are two things related to this. One is for every memory access, how many bits you're reading. That has to do with the configuration of your DIMM slots, the DIMM, which is a dual inline memory module. Okay, so the DIMM slots are configured in a certain way, so you can have like a most motherboards have four slots. If you populate only the first and the third slots, then you only have like one half of it populated, and I think that affects the width of how many bits you're reading per memory access. So that's the first number. Yep, that's not the case. hmm And Apple has an answer to that. I'll talk about that too. Yes, go ahead. Yep, yep, on the same die. Yep, is a what? SOC. Uh, cannot remember the abbreviation. What is SOC again? System on chip. I think Apple is still not entirely system on chip, but it's close. Anyway, getting back to double data rate. So that's one thing. Okay, how many bits are you reading per memory access is one thing, and then how big of a burst, okay, how many locations per burst you're reading, that's the second thing. I cannot remember the specs, of the modern day computer anymore. I think it's usually in the order of like 512 bytes or something like that. Okay, it's reading a whole chunk of memory, and that is read into the cache of the processor. So every time you update the cache, it's updating by a whole chunk. So how is that important from your perspective? Yes, it's reading into the outermost portion of the cache. So, okay, so getting back to how this is relevant to you, it has to do with the algorithm you choose to use. Okay, so let's just say that you're trying to sort an array. Okay, and if you have taken CISP 360, have they talked about quicksort? Yes. Okay. So quicksort is quick. Okay, it has an order of log n log n. Okay, it is the from the time complexity perspective, it is as fast as it can go. It is as fast as merge sort. Okay, how many people know what is merge sort? Some of you. Okay, very good. But there are also two versions of merge sort. Okay, there's the recursive version, and then there's the non-recursive version. So the main difference is the non-recursive version of merge sort. When you look at the memory access pattern, it is still kind of random. Okay, it goes like it goes to many different locations that are not contiguous, which means the burst mode reading is not helping you. Okay, you might be reading in 512 bytes at the same time, but when do you need to access the rest of the 512 bytes other than the 8 bytes that you're reading right that you need right away for comparison? Oh, it's not going to be for a while. So that means your cache can may not be fully utilized when you are using the recursive version of merge sort. The non-recursive version of merge sort accesses an array in a sequential way. In other words, it's just going down the array by incrementing the index sequentially. So that means a burst mode read and a burst mode write fits right into exactly what the algorithm needs to do. Now, do you really need to understand all the way down to the burst mode read and write operation to to really select a good sorting algorithm? Generally speaking, no. Okay, but if you really want to squeeze the last bit of performance out of your hardware, the answer is yes. All right. So this is kind of interesting, okay, because it does have a lot of impact to the actual benchmarking of an algorithm. Because if you factor that in, okay, the burst mode reading of DDR, you can actually get it working a lot faster. Okay. So getting back to this thing here, so let's just say that we are now done with this operation, by the way, okay, because you can see that location DC is now updated to BA. So now let's say we want to read from location 01, okay, which has content of 000. So we want to do that. So now let's go ahead and do that. Okay, so this is going to be interesting because we will encounter some problems. So right now, let me document what I intend to do. So I want to read location 01 and say, okay, what is at that location? That's what I want to find out. So the way to do that, not too hard. Location 01 means we have 0000 as my address. This is a read operation. Okay, let's go do that. And then the processor goes like, I cannot do that. We see red wires. It's a bad thing, right? So why do we have the red wires in this case? Yes, one part wants to specify one value, the other part wants to specify a different value. Okay, So let's find out what each part wants to do. So the only way I can do that is to kind of cut out a portion of the circuit, at least for the time being. So I just have to cut out this particular part here. So now that I have cut out that portion, you can see that, oh, so the D port wants to output all zeros. Well, that's not surprising because all the locations are zeros except for the few locations that we have been modifying. But the input pin is still specifying what we were doing in the right operation. So when you have these two wires joining, then all the zeros are fine because they're in agreement, but all the one locations are now conflicting with each other. So this one conflicts with the zero coming from here, and that's why it reports as an E or as an error. Yes, it is. So I think I get your idea. It is not called a multiplexer. It is called a clutch. No, it's not really called a clutch, but it does the job of a clutch. You can use a multiplexer, but you don't. But the okay, but the demultiplexer is still a one directional thing, which means once you want to. Okay, so the demultiplexer are you demultiplexer is one input, multiple output. So where are the two outputs? Yeah. So the proper solution is what we call a controlled buffer, which is basically a clutch. And I know all of these analogies are completely outdated because nobody drives a stick shift anymore. Yeah, not true? Okay. So you know what is a clutch, okay? So a clutch is really helpful in this case, okay? So I have to direct the clutch in the right direction. So I think we have to make it point south, and then we'll also make the control line to go to the other direction. All right. So now let me explain what is a controlled buffer. So a control buffer is not a multiplexer. Okay, it all it does is to copy whatever is the input pin to the output pin. But you can also use the control pin to say, don't do anything, make the output float. In other words, even though there's input, you can say, okay, don't do anything on the output port. Okay, make that float. So that is how we're going to solve the problem. Because what we do is we put this in here, and then okay, fine. I forgot to turn it into an 8-bit thing. Okay, there we go. All right. So now what we do is we say if the LD is a 1, then we want to disable the output of the control buffer. Then you go like, but that's opposite. That's opposite to what the control buffer does because the control buffer says if this control is a 1, then we want to output at the output port. Well, okay, nothing we cannot fix using a NOT gate. So all you need to do is to put a NOT gate here and you negate the LD signal before it goes into the control of the control buffer. So now you have it exactly opposite, okay, which is exactly the way we want it. And now we can finish this whole thing here and stash it here. And now we don't have a problem. Because in this case, when we are reading, we are disconnecting the input pin from the output pin completely. Because the control buffer says, yeah, there's input, but I'm going to turn the output into all floating lines. Yep. It's like a what? It's not a flywheel. It is just it's a simple way to disconnect something when you need it to be disconnected. You can also think of this control port as a component that is built into the multiplexer and the demultiplexers. That is what the when the multiplexer is disabled, remember you can either specify zeros or floating. The floating is done by a control buffer. It's basically a built-in component to the multiplexer and also the demultiplexer. So are we good so far? All right. So that's about it. Okay, today we covered the demultiplexer, we covered the RAM component. The ROM component was already covered on Tuesday's lecture, and those are the three components in today's lab. So now we have, we still got plenty of time to get into how the processor works. Okay, so it's going to take a little bit of time before you guys are used to how the processor works, but we'll go ahead and just kind of give it an attempt first. Okay, so we'll go to the processor chip here. And I know it looks really ugly because it is kind of complicated. Okay, so the question is, where do we start? Okay, there are so many components, so many wires, and so on and so forth. So the general way to solve a problem like this, okay, when you look at something that is super complex with lots of wires, components relying on each other, and so on, the first component that you start with is the one that does not depend on anything else. Okay, so you have to look for the one component that does not depend on the output of something else. You go like, okay, since this one does not depend on anything else, we're gonna start with this one. Does that make sense? So this is one way of analyzing problems is to figure out the dependency of the components that are involved in the problem. And then at least you will have an understanding of, oh, okay, now I understand this depends on this depends on this, and so on and so forth. That is a good starting point, is just to analyze the dependency of the things involved in the problem. Okay? So now that we know the technique, I'm not gonna have you guys to try to analyze which component does not depend on anything else. I will point it out to you. This guy here, the microcode pointer. So it is. I know it looks like a U. It really is a U, but it's a U because I cannot type in mu, the Greek letter mu, which is how you specify micro, which is small, right? So this is called a microcode pointer. Ucode pointer is the microcode pointer. You might say, but it still relies on a bunch of other things. Well, it really does not, okay? Because when you look at all the inputs here, it is always enabled, okay? This is the enable line, which means it's always enabled. But this is the only Oh, this is not good. I think we are still good, okay, because I just got a message from my Bluetooth headset that says your battery low, please recharge. I think we are good because we have finished all the important topics today. So even if it has to kind of crap out, which means I can still use the mic on the computer itself, but it's not going to be as good in terms of sound quality. Anyway, this is the only register that triggers on a falling edge. Okay, so right now the clock is a low, so the next transition is going to be a rising edge, which means this register is going to stay put during that transition. Okay, all the other not transistors registers. Okay, but all the other registers in the entire system, they're all sensitive to a rising edge. So that means while this register stays put on the rising edge, the other registers, if they're enabled, they're going to do stuff. Okay, so that's why we're going to start with the microcode pointer, because we know it is staying put. It does not rely on anything else. So now the question is, but what does it do? What does it do? Well, then we analyze the output. The output of the microcode pointer goes to an adder circuit. Okay, so this kind of circuit we have seen already when I talked about the counter thing. Okay, so we have seen this already, but it also goes to the A port of this ROM here. The content of this ROM is called microcode. Okay, so you might want to write that down. Okay, the content of the ROM of the processor is called microcode. The reason why it is called microcode is not because they are short. In fact, they're pretty long. Okay, if you look at the bit pattern here, they're pretty long. It is called microcode because each location of the ROM specifies a small step in order to execute normal code. So you have two kinds of code: the code that lives in RAM and the code that lives in this ROM. The code that lives in RAM would be the output of a compiler. and you can load it, you can change it, you can execute any program you want. The microcode that is in ROM, each one represents a small individual step in order to accomplish what a single code that you store in RAM needs to perform. Is that okay? Yep, go ahead. So we will take a look at what these bit pattern is are specifying in just a little bit. But in each location of the ROM represents an individual step that exercises certain components in the processor to get a simple thing done. Yes. So it has to do several things. Okay, so we're going to focus on just location 000 of the ROM, and then we want to know, okay, what does it actually specify? Okay, it has a content in hexadecimal of 1080007. Okay, so the idea is it is broken up into individual bits. Okay, if you look at the individual bits here, we got a splitter. We got two stages of splitter, by the way. So we have one stage of splitter, which is here, and then we have a second stage splitter, which is here, to chop those output bits of the ROM into tiny little chunks. Okay. So now the question is, I can see that it is broken up into a whole bunch of stuff. So where did they go? So now I am going to introduce the other components of the processor. There are only, even though it looks really complex, there's a lot of stuff in here. But when you think about, what can actually do something that is useful, there are only a few. You might want to write this down too. The first one is the program counter. It is a register, okay? But for this particular operation, do we have to be concerned about the program counter register? Well, not exactly because it's not updating, okay? But is it actually involved in this operation? We don't know yet. In other words, I know the program counter is not getting updated, but is somebody using the output of the program counter? That I cannot tell from just looking at the program counter, okay? So the program counter is one. The register bank is the next one. It has four registers inside the register bank, A, B, C, and D. I don't see anyone being enabled, which means I can also come to the conclusion that none of the four registers in the register bank is updated. But is anyone using the output of the register bank? I cannot tell right now. Okay, but these two are important components of the processor. And then we move on to the ALU. Okay, the ALU is not enabled because it has its own enable pin. Now, if the ALU is not enabled, you can kind of ignore that entirely because it simply means, oh, we are not doing any calculation. There's no addition, no subtraction, nothing like that. Okay, so now we move on to another register. So there's another register down here called the instruction register. Aha, I see a bright green line going into the enable, which means the instruction register is going to update on the rising edge. Remember, every register is updating on the rising edge except for the microcode pointer. That's the only one that updates on the falling edge. So now we look at this and go like, okay, so what is in your mind, knowing that the instruction register is going to update on a rising edge, and we are about to have a rising edge? What is a natural question to ask? Who is supplying the data to update it? Okay. Yes. Nope. 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 So how do we update a register? Which port specifies the new content of a register? Okay, we got one D port. That's right. Okay, so we click on the D port and then we say, who can possibly be supplying the new data that we are using to update the instruction register. So you have to do a little bit of tracking here. I remember as a kid, I like to solve these kind of puzzles, where there's a line going to everywhere. It's basically solving a maze. Okay, so we check out this thing here. This is an output pin. It does not influence the other things connected to this wire. So we look at the other connections. Okay, so we look at this connection here. This is a multiplexer. This is the input side of a multiplexer, which means it cannot possibly be outputting anything. Same thing applies to this one. So that means these are dead ends as far as our analysis is concerned. And then we see the line also goes to the D port here. Okay, so then you look at the D port here. This is the RAM component. Can somebody tell me, one, is the RAM component active? It is because SEL or select is a 1. Okay, it is enabled. Two, are we reading from RAM or are we writing to RAM? We are reading from RAM because LD is a 1. Oh, okay. So now we know the RAM component is supplying the data that we need to update the instruction register. So what is the next question? So we have figured out two things. One is the instruction register is about to update. We know the D port of the instruction register connects to the D port of RAM at this point. We also know the RAM is active. We are reading RAM. So what is the next question to ask? Who is specifying the address? Very good. So who is specifying the address so that in other words, who's telling me to read from location 0? So what do? Well, it's just like tracking down. You just click on this line here, and then you do the same analysis. Okay, you go like, okay, it goes to uh, an output pin. Okay, once again, output pins are not really particularly useful. It just reflects the value of a wire. But it also goes to a multiplexer. Okay, it's coming from a multiplexer. This is the output end of a multiplexer. What is the next question to ask? Before we look at the inputs, what do we ask first? Yes, this one it doesn't have an enable pin, so it's always on. Okay, but that's a good question. In the event that it has an enable pin, you want to ask, is it enabled? But since it does not have an enable pin, it is by default always on. So given that, what is the next question to ask? Yes. That is correct, okay? Because it has two input pins, it's a multiplexer, it has multiple input, one single output. So the question is, which input connects to the output, and how do we answer that question? Yes, because the gray dot, okay, the select is a one. So that means input one connects to the output in this case. So now we track only input one, okay? Your input zero is irrelevant in this conversation. Aha, is coming from the program counter. The job of a program counter is to remind or is to keep track of what is the address of the location of the next opcode to read. I'll say that one more time. The job of the program counter is to keep track of what is the location of the next opcode to read from RAM. So an opcode, you can see it as the opposite of a microcode. An opcode is a very small byte pattern, but it can potentially specify a complex operation. So you can, yeah, go ahead. hmm so getting back to Thomas the Tank Engine, this is the island of Sodar, and I'm the fat conductor, okay, because I cannot call anyone else fat, but I can call myself fat. So I'm the fat conductor, and I want to say, hey, where am I supposed to get the next operation to perform? This is the fetch cycle of instruction execution. You might want to write that down too. It is called the fetch cycle of the execution of an instruction. We are basically going to RAM, read a location. The content of that location is an opcode that specifies what are we supposed to do next. Yes. Nope. No, the PC has a zero because it is reset to a zero when we reset the processor. The microcode is only responsible to deal with the multiplexers, enabling the RAM, specifying a read operation for the RAM, enabling the instruction register so that it would update. It is responsible only to set up everything. It's like, oh, this switch, railroad switch needs to go to the first output. That switch has to switch this way. And by the way, turn on the factory because you're going to get something to process. And then also, whatever you're unloading at a dock, put it onto this train and then go. Yep. Yes. Well, we are only reading the opcode, so the opcode itself also would go to a different location in the ROM in order to re-specify everything. It's like, oh, this register goes to this input of the ALU, this register goes to that input of the ALU, and then the ALU is supposed to perform this operation. The output of the operation goes back to a specific register. So that is the whole thing. All right, well, it is 6:50, so you need your access code for the assignment for today. And I need to find out where my browser is. All right, so we are on this one, which is more processor components. And the access code is TTP. So lowercase TTP is the access code. TTP stands for Tax Toy Processor. Alrighty, I'll see you guys back there. And okay, so the recording is all good. Even though I'm running low on battery, the mic is still picking up, so we are good in the entire lecture today.